don't think I remember that.
Yeah, that's like
Mr. Park,
serving in the military.
did I finish your test correction?
We didn't have test corrections, remember?
I got something wrong.
Oh, now Hong doesn't read the email.
Oh yeah,
No,
I
no,
read
no, I
the
did.
email. Oh my
I did, but
god.
you still have, I thought you still have to do it sometime.
It was like Christmas present.
Okay, you guys want to do that?
No, it's okay. We're good.
Josh.
I always see what I got wrong.
Josh, Clark. Joshua.
Didn't we pass out the test?
Yeah.
One time.
Yeah.
We only had like 1 minute.
Okay, let's do what we gotta do here.
Like,
Okay, mathematical induction. This is another way to prove things. And we usually use it when you have to prove something is true for all positive integers or natural numbers. So here, this is the concept of mathematical induction. So suppose you have a statement that you want to prove true for all positive integers. So the first thing you do is you show that the statement is true for 1. And then here's the key part of the proof. Then you have to show that if the statement is true for any integer, then it will be true for the next integer.
Yeah.
And therefore, it works for all positive integers. Because look, if you show that it works for 1, then this statement says, well, if it is true for 1, then it's true for 2. But then if it's true for 2, it has to be true for 3. If it's true for 3, then 4. If 4, then 5. If 5, then 6, dot, dot, dot. Therefore, it's true for all positive integers. All right, so let's take a look. I'll do one of your homework problems for you. Number 1 is easy. 13 or 14 then. Which one do you want to do?
14.
No, because that has the most algebra. So
13.
I want you to do that. Okay, 13. 13. A plus AR plus AR squared plus dot 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 plus AR to the n minus 1. And what is that? That is the sum of a geometric series, right? So this is the sum of the terms of a geometric series is equal to the first term all over, that's not right. Equals first term, 1 minus r to the n, all over 1 minus r, right? The sum of the first n terms of a geometric series. So this is your statement, P of n. So the first step, show that P of 1 is true. Well, what happens when you plug in 1 for n in this formula? You would get, because if you plug in 1 for n here, you're just going to get AR to the 0, which is A. Is that equal to A times 1 minus R to the 1 all over 1 minus R?
Yeah.
Yes, so we know that this is true. And then here's the most important part. We have to show that if the statement is true for any integer, then it will be true for the next one. If it is, then it will be true for the next integer. So how do you form the statement P of k? Well, if this is P of n, P of k is simply just, actually you can just use n if you want. You don't have to use a different letter. Plus dot 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 plus AR to the k minus 1. That's equal to A 1 minus R to the k all over 1 minus R. Basically, you simply plug in k for n. Okay, now, what is the statement P of k plus 1? What would it be? It would be A plus AR squared plus dot 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 plus AR to the k minus 1 plus. So basically, it's like you're adding one more term, right? And what would be that next term? AR to the k, right? Equals A 1 minus R to the k plus 1 all over 1 minus R. Basically, you're substituting k plus 1 for n. That's what you're doing, right? So this is what we have to show. See how we have to fill in the things here. If it's true for this, if this is true, then this statement has to be true as well. So basically, you're just going to use algebra to show it. It's not difficult. So what can I do to this equation here so that I can get this one?
Substitute. Oh, never mind.
Well, if you look at the left side of the equation, the only difference is this, right? So simply, why don't we add this to both sides of the equation? So a plus ar squared plus dot 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 plus ar to the k minus 1 plus ar to the k is equal to a 1 minus r to the k over 1 minus r plus ar to the k. So we simply added this to both sides, right? That's because we want to make the left side of the equation look like the left side of the equation here.
Yes.
And then now all you have to do is use algebra to show that this is the same as that.
Why is it K not N?
Huh?
Why is it N turn K?
Because it's P of k. I mean, that's just the way it is. But you don't have to. You can just do P of n and P of n plus 1 if you want.
Why is that just A?
That's the first term in the geometric
So if
series.
it's like P of 2, that is A plus AR,
Yep.
and you don't know R?
Yeah, R is the common ratio.
Yeah, but like, in this case, you just assume. Oh.
Okay, you remember the formula for geometric series? Well, this is it, right? The sum of the first term of a geometric series is equal to that. But we need to show that it doesn't just work for like add the first term, the first two, the first three, or the first four. We have to show that it works no matter how many we add together, right? And so that's why this is perfectly set up for mathematical induction. So we did the first step, you understand that? Plug in 1, does it work? Good, yeah. Okay, now we have to show that if it's true for any integer, then it will be true for the next integer.
Yeah.
Okay, so like I said, if it's true for 1, then it must be true for 2. But if it's true for 2, then it must be true for 3. If 3, then 4. If 4, then 5. And then it covers all the positive integers, right? Okay, so,
So you equate them.
no, this is P of n is this whole equation. It's the whole equation. So now we have to show that if this statement is true for any integer, then it will be true for the next integer. That's our job. So this is P of k, or if you want to put n, you can. This is P of k plus 1, or if you want to put n plus 1. So you have to show that if this equation is true, then this one is true as well. And then, like I said, you're just going to do algebra. So why did we add this to both sides? Because that's the left side of the equation here. We want to get from there to there. Okay, next step. Oi. Okay, now, how do I add these together? Least common denominator?
Yeah.
Okay, so least common denominator, so what goes on the top? A minus AR to the K plus AR to the K minus AR to the K plus 1, correct? A, but these cancel out, and if you factor out the A, don't you just get this? So therefore, if this statement is true, we don't know if it's true, but if it's true, then doesn't this one have to be true? Because we just simply added the same thing to both sides, and we just did some algebra, right? And therefore, this statement is true for all positive integers.
But you didn't prove that.
No, we proved that if this statement is true, this one will be
Oh,
true.
you don't have to prove that it's true though.
Well, that's what we're trying to prove.
Oh, we're not done.
No, well, we're done because we showed that it works for 1. Because if it works for 1,
Oh.
then this thing here shows that it has to be true for 2.
Oh.
But then now that we know it's true for 2, therefore it has to be true for 3.
Oh, yeah.
And then if 3, then 4. Muy bien.
Mr. Road.
What's it fun?
I don't know why. It doesn't sound funny. Okay, and then look, look, these are all formulas that we learned in our math career, right? The sum of squares, the sum of cubes, and then you got this is some number theory ones over there.
Yes.
No, I don't know what it says on the assignment sheet, but we're gonna do the Euclidean algorithm and the Chinese remainder theorem today. Let's put it up on the big board.
Alright. Español.
Okay, so the Euclidean algorithm, this is obviously by Euclid again. This is a method that you can use to find the greatest common factor of two numbers. Or they call it the GCD, the greatest common divisor. Same thing, right? Greatest common divisor, greatest common factor. Okay, give me two numbers that are kind of difficult to find the greatest common factor.
37.
So 37,
I see.
37 and 512. Okay, one. Because that's prime. You don't want it to be a prime number.
Sorry. My English is
487
weird.
and prime number.
587.
400.
Just use an even one.
Yeah, let's just do some. Okay, gotta be at least digits long.
386.
Okay, now think of a number that has like a lot, that's abundant. It has a lots of factors.
484.
512.
You guys, okay, I used the word abundant. You guys remember that from PCH?
Numerous.
512.
Okay, let's go back to PCH. Remember we learned about perfect numbers in logic?
Oh yeah.
What is a perfect number again?
625.
A number whose proper divisors add up to itself. So 6
Oh.
is the first perfect number, because what are the divisors of 6?
1, 2,
Proper divisors. So that means it doesn't include itself. 1, 2, and 3, right?
Yes.
And then look, what happens when you add them up? You get 6.
Oh.
That's why it's perfect. You know what the...
Good though.
Hmm?
Yeah, that's a good question.
Why is that different?
Why is that what?
Why is that different factor? Is there like a lot of factors?
Wait, I'm trying to hear her home here.
Is it good if like it's perfect digit have like a lot of factors?
No, it's just somebody noticed that, hey,
That's a
it comes out
good
perfect.
Why is that good?
No, well, actually, it is. Wait, okay, just for that, you're gonna get the lecture on perfect number. What is the next perfect number? 28. Okay, but that's because the sum of its proper divisors add up to itself. What are the divisors of 28?
1, 2,
1, 2, 4, 7, and 14, right?
Yeah.
So all the divisors except itself. And then what happens when you add them up?
28.
You get 28. It's perfect. You know what the next perfect number is? 496. And then what's the next one? 8,128. What's the next one? 33 million.
How do you
Million.
550,336. Did I remember it correctly? Because I got the perfect number eye chart over here.
Wow.
Yep, I remember. Well, I can only remember to there.
I thought that was the 2 times product.
So Hong was asking, well, what's so good about perfect numbers? Is that what it is? Okay, do you guys remember what a Mersenne prime is?
Yeah.
To the n.
2 to n minus 1.
Yeah, so 2 to the n minus 1. No, I think we should use p. Okay, if p is a prime number, and you plug it into this, and you also get a prime number, then we say that this number is a Mersenne prime, named after the mathematician Marin Mersenne. So let's start with 2. If p is equal to 2, you get 2 to the 2 minus 1, which is 3. Is that a prime number?
Yeah.
Yeah. So we say that 3 is a Mersenne prime. It's not just a prime number, it's a Mersenne prime. What about when p is 3? 2 to the 3 minus 1 is 7. Is 7 a prime number?
Yeah.
Yeah, so 7 is not just a prime number, it's a Mersenne prime. What about when p is 5?
No bueno.
What?
Oh, muy bien.
31. 31. Is 31 a prime number? Yeah, so 31 is a Mersenne prime. What about when p is 7? 2 to the 7 minus 1, what is that? 128, 127. is that a prime number? You guys don't remember this on the PCH test?
I remember the name.
I put this on the PCH test. So is 127 a prime number?
C.
Yes.
Yes, so 127 is a Mersenne prime. Let's just do one more. What about when p is 11? 2 to the 11 minus 1. So 2 to the 10th is 1024. So 2 to the 11 is 2048 minus 1, 2047. Is 2047 a prime number?
C.
No, it's not. You know why? Because it's equal to 89 times 23. That was on the PCH test. See, you guys just. Anyway, so, well, that's not a Mersenne prime because it's not even prime. Anyway, that's how you get Mersenne primes. Now, what do Mersenne primes have to do with perfect numbers? Because people were obsessed with finding perfect numbers, yeah? So, Euler, he proved this, I don't know how he did it, but he said, if you have a Mersenne prime, and you multiply it by 2 to the p minus 1, like this, you will get a perfect number. Yeah, so what about when p is 2? What happens when you plug in 2 for p here? Plug in 2. 3, and then plug in 2 there. Times 2, you get 6. That's a perfect
Oh
number.
my god, what is it?
Okay, plug in 3. What happens when you plug in 3?
7.
7 times 4 is 28. That's a perfect number.
Oh my.
Okay, what about 5? 2 to the 5 minus 1 is 31. 2 to the 4th is 16. Multiply that together. 496. You get a perfect number.
Oh my god.
So I don't know how he did it, but Euler actually proved that, yeah, if you have a Mersenne prime,
Wait.
you multiply by that, you will get a perfect number.
Whoa.
I don't know how, this is crazy how anybody could do it. Do you know Euler, when he, I don't know what age, but when he was older, he became blind.
Why?
So he did lots of the mathematics he did it while he couldn't even see.
Oh, that's
I
like
don't know what to-
Beethoven.
Exactly like Beethoven. He composed music, but he was deaf. Why are we talking about perfect numbers? Oh, because abundant. Okay, so what is a perfect number? That's when the sum of the proper divisors add up exactly to the number. So what do you think about if the sum of the proper divisors are less than the number? Like for example, 8. What are the proper divisors of 8?
1, 2, 4.
What? 1, 2, and 4? What happens if I add that up? It's less than 8. So we say that 8 is deficient. It's a deficient number. Perfect, deficient. But what happens if the sum of the proper factors is greater than the number? For example, 12. What are the proper divisors of 12? 1, 2, 3, 4, and 6. That's obviously greater than 12. So we say that 12 is an abundant number. I believe this is the PCH lecture in logic.
Why is it?
Gone from the memory.
I know, we did Mercedes something prime.
And this was on the PCH test right here.
But we didn't do
Because remember, you have to write the negation of the statement, and then you have to determine if the original statement was true or false.
Yeah.
And then a lot of people, they just put true and then -2.
Was it the
How would you
last
keep
question?
telling your brain like, oh yeah.
Okay, why are we even talking? Okay, now let's do the Euclidean algorithm. So how can we find the least common divisor or least common factor, not least, greatest common factor of two numbers, especially when they're big? So this is something you could program a computer to do. Okay, so let's think of a number that has lots of factors. That's why I said abundant, yeah?
496.
666.
Okay, but that would be 2 times 333. So 100, okay, that's not bad.
Yeah,
That's not bad. Okay, so 496. What is the greatest common divisor of 490? Let's put the big one first. 666 and 496. Now, of course, you can do this easily without any kind of algorithm, right? You guys learned how to do this in elementary school. But like I said, what happens when the numbers are big, then you probably want to use a computer to program it, and then we do this. So look at the Euclidean algorithm. If, and again, we're talking about positive integers, yeah? If a is equal to bk plus r for some integer k, then the greatest common divisor of a and b, that's this and this, is equal to the greatest common divisor of b and r. Okay, read that again now. You guys gotta learn how to read mathematics then.
Oh, there's a whole number.
What?
We're only talking about positive integers. That's what number theory is pretty much, the study of the positive integers. Okay, so this is how you do it. 666 is equal to, okay, b is 496 k plus r. Okay, let's put in some positive integers here.
One.
Just one.
Well, this one's gonna be 1. And then what is 666 minus 496?
170.
0, okay, 170 here. So therefore, the greatest common divisor of this and this is equal to the greatest common divisor of 496 and 170. See, and the numbers are smaller, right? You keep on making it smaller at each step. So you do the same thing then. 496 is equal to 170 times something plus something.
3. No, 2.
2, so 496 minus 340 is 156?
Yeah.
2.
And then you just do it again.
2.
So therefore, the greatest common divisor of this and this is equal to the greatest common divisor of 170 and 156 then, right? Do it again. 170 is equal to 156 times something plus something. 1 and 14. So the greatest common divisor in this and this is equal to the greatest common divisor of 156 and 14. Okay, let's just do it one more time. Maybe. So 156 is equal to 14 times something plus something. 11 plus 2. So that's equal to the greatest common divisor of 14 and 2.
2.
Yeah, 2. Okay, that wasn't that exciting. Who picked these numbers? I thought 666 was going to be good, but it apparently wasn't that good. Anyway, this is called the Euclidean algorithm. You know what I should do on the test? I should give you guys some really big numbers and let you use your calculator.
No.
Why not? Why? Okay, so you guys will determine tonight's, okay, so the first homework problem for tonight is, besides that, find the greatest, using the Euclidean algorithm, of course. Okay, let's pick some really good ones now.
6,666.
Wait.
Stop with that already. Stop. Okay, 2 to the 10th, because you know when you find greatest common divisors, you prime factor the number, yeah? So how about 2 to the 10th times 3 to the something? 3 to the 4th?
Yes.
81.
Alright.
So we're gonna know the answer before we even do it. 2 carry 3 carry 1. I hope I did this right. 4, 4, 9, 2, 8. 82,944. Don't put the comma there then. And then,
5040.
how did you, okay. Shall we trust?
No, what about
5040?
Yes.
Okay, that's problem number, so you, okay. This is the Euclidean algorithm problem on tonight's homework. I'm gonna call on you to see if it's right.
Oh, bruh.
Oh, bruh.
Okay, now the Chinese remainder theorem. Okay, you guys read that and then see if you can make anything out of that. Okay, so this is what you're gonna do, because I gotta use the bathroom. You read this, and then you know the problem you took the picture of.
Yes.
Put it on the board, and we're gonna start doing it.
We solved it.
97.
Yeah.
You solved it using the Chinese remainder theorem.
Yes.
How did you guys know what the Chinese remainder theorem is?
They're smart.
MVC.
You looked at that.
No.
Because I was thinking, you know the thing you were writing on the board the last time?
Yeah.
That was this, right here. You were doing this.
Yeah.
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 Do I put it on the board?
Yeah, because everybody else needs to see it. I'll be back in a minute, or two.
Wait.
What is the Chinese remainder?
Like, so that x congruent to a, like, so like, that's like x divided by a number, then you get like a1. So if you have like a system, like how you kind of like,
Wait, Josh, can you just like show how you did it, like with the numbers? Because I did it way, but I took way longer than this.
no, I guess because I used to calculate.
Wait.
Oh, okay, so.
Wait, no. I feel like I'm missing some steps in mine because I had to do a lot of stuff by hand.
Like,
X is
So the
equal to.
factors are the, and then the.
Try to write out how you did it on the board.
I have no
I
skills.
just did it like that.
So it's just like that.
No, like write it out.
Write
Try.
like this.
I forget how I did it.
Because here, I'll show you how I did it, but it was like,
Theorem.
it was hard. No, it was like really hard.
So you use all the
Oh,
times divide by
Okay, so
two,
it's
and 5, 7,
2
so you get
times 3
1 and 2 and 3
times
and 4.
5 times 7 times blank.
And then you do this.
Yeah.
I don't know, I mean, I haven't done it yet.
Me neither.
So what are you asking me? They're blanking like each one.
I'm studying it with you.
Studying, I haven't done it yet.
7, 11.
I'm learning it with you.
It's
3, 5, 7, 11,
crazy.
right?
Okay.
So you see what I did, right?
Yeah.
So basically, okay, so if you look at this one, 2, if you divide this by 2, you get a remainder of 1.
Wait.
All of these terms are divisible by 2 except for this one.
Okay.
So basically, you just have to fill in this blank.
So you can divide by 2.
No, you have to fill in this blank such that if you divide it by 2, you get 1. You get a remainder.
real? That's it?
Yeah, and then for the next one, you look at this thing,
That's so
3.
cool.
All of these are divisible by 3 except for this one. So you just have to fill in the blank so that you get a remainder of 1 for 3. And then for this one, yeah, all the
Such a
way.
genius.
Damn.
Yeah, that's how you do it.
That's how you do it? Yeah. Why did it take me so long?
It's just
So that's
because
hard,
I calculate.
isn't it? How'd
But
you
then,
find all
but
of
then
them?
all of these, it will give you your answer in like mod.
No, yeah, it's not, it might be not simplified.
Yeah, it'll give you your answer mod 2 times 3
Yeah.
times that. So then you have to subtract that until you get the lowest number
Oh, that's
where it gets negative.
Damn.
3. That's not what I wrote on the board.
It is.
2 implies 1.
The
3 implies 1.
minus 2, and there's 1 left.
Yeah,
Oh, yeah, you, it was.
Yeah, that's how you wrote that.
I wrote that on the board?
Yeah.
Okay, and then you guys said, what did you guys say?
Minus 7, I think?
Minus 7, yeah.
Okay, somebody, because of this 11, the number's gonna get big, so somebody needs to like, when I tell you to punch in a number, you tell me what it is. Who should we pick? Somebody that doesn't do the homework.
I got it.
Okay, so on the video, I'm thinking of, I have a number of eggs in my basket. If you divide the number of eggs by 2, there's 1 remainder. If you divide it by the number by 3, you get 1 remainder. Divide by 5, you get 2 remainder. Divide by 7, you get 4 remainder. Divide by 11, you get 5 remainder. What's the smallest possible number of eggs I can have in my basket? Okay, you're gonna get this problem on the test, but I think I'm only gonna give you 4. Well, first of all, the numbers have to be pairwise prime. You know what that means? If you do take it by pairs, they're all relatively prime like that. So in other words, you can't have like a 4 and a 6 there.
Sorry, what does that mean?
So simplified.
Right. See, it says pairwise relatively prime. You know what, okay, what does it mean if two numbers are relatively prime?
6 and 7, isn't it?
Yeah, that means they're, the greatest common divisor is 1 then, right?
Not everything has to be prime.
No,
Oh,
they
okay.
have to be pairwise prime. So you could, like, since this is the only even number here, that could be a 4 or an 8, but it can't be 6, right?
Yeah.
Because 6 and 3 are not relatively prime.
Then you just use 1, 2, and
Okay. Okay, so you started writing this on the board? Okay, so you gotta learn how to read math, okay? So let M1, M2, all the way to Mn be pairwise relatively prime positive integer. So this is M1, M, so this is the M's then, right?
Yeah.
M sub i's then. And let A1, A2, A dot 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 be any integers. Given the system, I wanted to write it on the same line here. Okay, we'll just squeeze it in. X is congruent to A1 mod M1. So that would be 2 then, right? And X is congruent to A2 mod 3. X is congruent to A3 mod 5. X is congruent to A4 mod 7. And X is congruent to 5 mod 11. Okay, given that system, let M, capital M, be equal to M1 times M2 all the way to Mn. And for each I, so what is M? 2 times 3 times 5 times 7 times 11. For each I, capital Mi is equal to M divided by Mi. So that means M1 is equal to M over M1, which is? So it's this number here divided by M1, which is 2. So basically this, yeah? 3 times 5, let's not use parentheses, 3 times 5 times 7 times 11. What is capital M2? That would be M over M2, which is 2 times 5 times 7 times 11. What is capital M3? M over M3, which is 2 times 5, 2 times 3 times 7 times 11, correct? M4 is equal to M over M4, which is 2 times 3 times 5 times 11. And finally, M5 is equal to M over M5, which is 2 times 3 times 5 times 7. Okay, move on to the next step. Now, for each I, find x sub I such that M1 times xi congruent to 1 modulo M1. So should we leave it like this, or should we multiply out this number?
Multiply out.
Okay, so
Human calculator. 1155.
you're not gonna let us down, right? 1155 x1. What does it say?
X1.
Oh, x1 though. X1 then, right? Make sure it looks like a 5. Is congruent to 1 mod M1, which is 2 then, right? Okay, let's just write out all the equations first. Okay, next one. Multiply these numbers here.
7.
Wait, let's see if I can do it in my head. 770.
Yeah.
770 x2 is congruent to 1 mod 3 then.
Yeah. That's 462, I think.
Okay, I trust you. 462 x3 is congruent to 1 mod 5.
I see 330.
330?
Yeah.
I'm trusting you now.
Yeah.
X4 is congruent to 1 mod 7. And then finally, 210?
Yeah.
X5 is congruent to 1 mod 11. So what you have to do is you have to find numbers that satisfy this. I guess and check, yeah?
Yeah.
So what could be a number for X1? Because of course there's going to be an infinite number, yeah? You just have to find one.
One.
Okay.
Try to make it smaller as small as possible.
First one just means odd, right?
Okay, 1.
Okay.
X2,
Oh, bruh.
could it be 1? 769 is divisible by 3. 7, 6, 9, no.
It's 2, I think.
2?
There is two.
So what is 2? 1540 minus 1. So 1539 is divisible by 3.
Yeah.
Yeah, okay, so 2 works. X3, let's try 1.
5.
Is 4? No.
Not
Yeah.
That's 3, right? 3.
Oh. Oh.
Because there's 460.
Yeah, 3. Right? Because 6 minus 1 is 5, right? And, okay, X4 could it be 1? Is 329 divisible? There's a divisibility test
Yeah,
for 7.
It's 1.
It is 1.
Yeah.
So is 329 divisible by 7? 329 divisible by 7?
Yeah, it is.
4, yeah it is. Hey, good. The smaller the numbers, the better. And X5 could be,
That's wrong. Wait,
okay, you guys know the divisibility test for 11, right?
I think 2 and 9.
Okay, let's go back to PCH.
You
Yeah,
You
so
add in
437,600. Okay, let's just do this number. Is this number, okay, that's bad. Okay, 2. Is this number divisible by 11?
Yeah.
Yeah, so starting with the first digit, add up every other digit. 4 plus 7 plus 2. Okay, then this is not right then. So I need a 4 here. Okay, now starting from the second number, add up every other digit. So you said 13?
Yeah.
And what do you get? 13. So if you subtract those two, if that number is divisible by 13, then the whole number, 11, then the whole number is divisible by 11.
Yeah.
2 and 9.
Okay, so now that we know that, so 209.
Yeah, that's.
Is 209 divisible by 11? Yeah, it is, right?
Yeah.
That's a 1. Okay, now that we got all of these xi's, what does it say to do? So let x naught, oh my gosh. Okay, let's do it up here. Let x naught be equal to m1 times a1 times x1.
Isn't it easier to just put those numbers in there?
Okay, what is m1?
What? Yeah.
1155 m, okay, capital M, lowercase a. Where's a? A1. Okay, what was A1 in this one?
1.
1, yeah.
That's over
Then
there.
it's 2.
The second
Yeah,
column.
yeah,
Where's the second column?
yeah. To your left.
To your
yeah,
left.
1, 1, 2, 4, 5.
Oh, these are the A's?
Yeah.
Where did that come from?
Because it's.
Oh, yeah. Okay. 1 times xi, x1 is there, 1. Plus, and you just keep doing this. So what's the next m? 770 times 1 times 2 plus, what's the next one? 462 times 2 times 3 plus 330 times 4 times 1, and then finally 210 times 5 times 1. Okay, Song?
That's 907 minus 10K.
No, just tell me what this number comes out to. Just tell me what this number is. Come on, step by step.
Let's raise.
You have a calculator.
I don't even know how to use a calculator.
I can take out my phone and do it faster than you then?
Well, how do you erase 1?
Oh no. Okay. Luckily Park is doing it too.
7837.
7837. Okay, just confirm it then.
Yeah. Oh no, 783. Oh yeah.
Oh my God. Okay, and thus, x is equal to x naught 7837 plus m. What is capital M? What is this number? Solve. Capital M.
That is
2310.
2310.
yeah.
2310. Wait. X naught plus mk for some integer k.
I also do.
And k is negative.
Okay, so what number, what integer can I plug in for k to get the smallest positive integer for x?
Negative 3.
Negative 3?
Yeah.
Okay, so 2310 times negative 3, 0, 3, 9, 6. So 7837 minus 6930. I guess I should have put an equal sign there. 7837 minus 6930, 709. So 907. Is that what you guys have?
Yeah. No.
Wait, what's your part?
Yeah.
Wouldn't it be easier to just put like those yellow numbers on the right into, instead of all the ones, and then just solve there?
Say that again.
Like,
Put these numbers here,
yeah,
the A's.
and put the A's in place of all those ones, and then just solve it just straight like that.
Oh.
And then what, just multiply them?
And then once you get all of the x's, then just times it into the, instead of ax, just do the x's. That's how I learned it. And I think it's easier because, for example, if you did that for x3, then you would just end up multiplying it by 1 instead of having to multiply by 6.
I'm not, I'm not exactly sure what you're saying. So you're trying to like make the Japanese remainder theorem then?
Yeah.
Is that it? No, but this is Chinese. This has got to be the fastest way.
Oh no, there's like a like a methodical way to solve the congruency.
Oh, you're talking about the,
Uh,
yeah, that weird function.
And
The
then
weird symbol
I forgot it, but it's like you make the Diophantine equation, and then there's a really easy. There's really easy.
Oh, you learned this before then?
Yeah.
Yeah.
Oh, you went to the camp then?
Yeah.
You guys didn't do it this way then?
No, we didn't.
No, it's, well, I didn't go.
Okay, so what problem are we gonna have for homework, Tom?
That.
You know what, maybe it's time I check homework. Okay, so this is, okay, you know what? I'm not gonna give you 5, because 5 just makes the numbers bigger, so I'm not gonna let you use calculator on the test. So I'm just gonna give you 4 then, so let's just change this. If you divide by 2, you get 1 remainder. You divide by 3, you get 2 remainder. You divide by 5, you get 4 remainder. And when you divide by 7, you get 5 remainder. Then how's that? Okay, this is, so here are your 2 homework problems tonight then. And then we'll see what kind, hopefully we can agree on the 2 answers. No, you can see that when you put the 5th one in, man, it's like way more work.
It's 89.
What?
It's
Be
89.
quiet.
Oh,
Be quiet.
How do you get it so fast?
Use a
I
V.
just
Okay, the directions are, use the Euclidean algorithm to get this. Use the Chinese remainder theorem to get this. So the only way I can thwart part then is I just gotta give big numbers and let you use a calculator then,
Okay.
right?
Yeah.
Wait, you can do that in your, what do you do in your head?
I don't know, I just think the
The
7,
biggest one.
and then, oh, like, the 2,
2 and 5
the
goes in.
1,
Oh, yeah. So take the biggest one and just take,
and then use the 5 and the 4, so you know it needs to be 9. And
It
then,
has to be 9.
so then, that already fulfills the first one, and then you just like try a couple.
2 has 1 remainder, so it's odd. It's
okay, I can figure out that one. But then you gotta do all 4 conditions, that's the hard part.
Well,
Yeah,
like
well, you know the one is-
if the last digit is 9, then
Okay.
1 and 3 are already satisfied. So just use 7 and just like try out.
Joshua Park has the mathematical prowess.
Oh, okay, yeah, but, okay, again, but what if the numbers are bigger?
Yeah.
Like instead of using 2, 3, 5, 7, oh, if you divide it by 220, well, what's a prime number? 220, I don't know, 7, you get 183 remainder.
Yeah.
Then it would be a little harder. So basically, you want to get something you can program a computer to do, yeah? Wait, now you're using phone.
I'm not using it. I just put it on
Well, when you look at it, you used it.
time.
You look at the time, you used it. All right, let's go home. Anyway, on the test, should I just give you the Euclidean algorithm and the Chinese remainder theorem? Okay, I will. You heard that, period 9?
Yeah, I'm sorry.
All right, bye.